Hi, in this video I'm going to talk about system of two first order linear differential equations. Okay, so you remember that in the last videos we talked about first order differential equation. It could be linear or nonlinear. What determines linear and nonlinear equations? If in the right hand side there is the product of the y variable, right? If there is like dy over dt, if there is, and on the left side, and in the right side, if there is y square or any exponent of y other than 1 on the right hand side, then that is nonlinear. Okay, so in this system of equations also the same concept applies, but first of all let me write down how does the system of linear first order ODEs look like. Okay, the system means there will be more than one equations. All right, so for example, let us consider a system of two first order linear differential equations. So dx1 over dt equals to p11t. It is like coefficient of x1. See, there is x1 plus p12t. This is p12, p11, p21, p22 are basically the coefficients of x1 and x2. So times x2 plus g1t. It is g1t. You see that this p11t, p12t, g12 may be function of t or a constant. Okay, not function of x1, not function of x1 or x2. So they are either constant or function of t. Similarly, dx2 over dt equals to p21t times x1 plus p22t times x2 plus g2t. Okay, so again p21, p22 are either constant or function of t, and g1t, g2t, they do not have x1 and x2. This is like a separate constant term or a function of t there. Okay, now you see that these two differential equations, these two variables are connected. Why? Because the rate of change of x1 depends on x2. You see that x2 is the second variable, and rate of change of x2 depends on x1, so they are connected to each other. Okay, and these are the initial condition. X1 at t0 is x10 and x2 at t0 is x20. Let us suppose that this system is denoted by a. Okay, now if there is x1 times x2 here, or here x1 square or x1 times x2 like that, that would be non-linear. Okay, if any of these terms have the product of x1 with itself or x2 with itself or x1 times x2, then that we will call that is non-linear. Okay, so if you write the matrix form of this, then you can write this, you can just combine into a single matrix, dx1 over dt and dx2 over dt. In the right hand side, what I'm doing is I'm writing the matrix of the coefficients only. So p11t, p12t, p21t, p22t times, right, x1 and x2, x1, x2 in the column form. Because if you simplify, if you multiply these two matrices, you will get exactly the same thing. How? p11t times x1 plus p12t times x2. Similarly, p21 times p21 times x1 times plus p22 times x2. That's what you will get. And then plus g1 and then g2. That is the matrix of the separate constant or the separate terms, not the terms without x1 and x2. Okay, guys. All right, so this is what you will get in the matrix form. And if you denote this by just dx vector, there is a vector notation, over dt, if you denote that by dx vector over dt, x is x1 and x2. So if you simplify that, you will get dx1 over dt and dx2 over dt. Similarly, if you denote this whole thing by a of t, this at is maybe function of t, the matrix of matrix depending on function of t for each of these entries, or just constant matrix, meaning I should not say constant matrix, a matrix of constant values, not the same numbers but just numbers there. Okay, plus gt is so x is a vector, that x1 x2 here, plus gt is g1t g2t, again that may be vector of constant or just function of t. Okay, and then this thing, this initial condition, you can write vector x at t0 is equals to x0, where x0 is x10 comma x20. Okay, where a is that, and then x is that, and then g is that one. Okay, so when we call this system is homogeneous, the system is homogeneous if there is no separate constant term. That is, if g1 is 0, g2 is 0. Homogeneous if vector g is equals to 0 vector, meaning that if there is not this term and that term, then you will have just x1 x2 x1 x2 terms only. Okay, so there will be p11 t x2 x1 plus p12 x2 p21 x1 p22 x2 p22 x2, but no separate terms, no terms without x1 x2. In that case we call that is homogeneous. If there is a separate term without x1 x2, separate term like a constant term or terms with t only, but I mean some terms with t but not with x1 x2, then we call non-homogeneous in that case. Okay, so again I discussed that already, linear versus non-linear. If the exponent of x1 and x2 are 1, and if they are not appeared in the product form, then it is linear, otherwise it is called non-linear. Now what we want to discuss next is in what is the condition that this system of equations have solution. Okay, because our goal in this chapter is how do we solve a pair of differential equation. Okay, a pair of linear differential equation. So that's our goal. So but first of all we want to know in what condition this pair of differential equation, I would say a pair of first order linear differential equation have solution. So there is a theorem. It says that let each of the function p11 p12 p21 p22 and g1 g2 be continuous if all these functions are continuous in an open interval I equals to ab, and let that t0, the initial time, be any point in that point I. T0 must fall in that interval, and x10 x20 are the initial values, are the numbers, then there exists unique solution of the system A. So if these terms are continuous, okay, in an open interval, and if that t0 fall in that open interval, then there exists a unique solution of this system. Okay, how would the solution look like? The solution will look like x1 is function of t, and then x2 is another function, let's say psi of t. The solution will look like that, and then you can write in like x1 x2 equals to some format there. Okay, some format there, but the unique solution will look like this. Okay, next thing that I want to mention is the system is autonomous if the right side of A does not depend explicitly on t. Okay, what does that mean? That means if right side of that system A, if all this right side does not have any t that is seen here, it may be x1 is depending on t, x2 is depending on t, that is fine. But if p11 p12 g1 p21 p22 g2 are just numbers, in that case you will see like 3x1 plus 5x2 plus 1, like that, right? So there is no explicit t there. So in that case we call this system is autonomous. Okay, otherwise it is non-autonomous. All right, in other words, if A and G have just numbers, if matrix A, in this matrix A and matrix G have just numbers there, then we call that is autonomous system. So we will talk about the finding the exact solution later, but to solve analytically we find equilibrium points first by setting dx1 over dt equals to 0 and dx2 over dt equals to 0, and then we will also draw this, we will also sketch the phase plane. What do you mean by phase plane and how do we draw it? To sketch the phase plane, pick various point x1 x2. So what we'll do is we will draw x1 and then x2, x1 versus x2, and we pick various point. Okay, various point x1 for various point, and what we do is we find out where the matrix A, that matrix A, this matrix A, transfer that point x1 x2, at least in the homogeneous case. Homogeneous means whenever there is no the right hand side function. Okay, so homogeneous case, the point x1 x2, and then after we find out wherever that that matrix x1 x2, matrix A takes x1 x2, and then from that point x1 x2 we draw a pointed line. So okay, as I mentioned, to it may be harder sometimes to find out the exact solution of the pair of differential equation. We will learn some techniques, okay? So usually what we do is we draw the direction field or the phase portrait. How do we do that? We'll find out the equilibrium point, okay? We'll find out the equilibrium point first, and then to check the stability of that, we will draw the direction field. And then we'll draw the several solution where it go, okay? All right, so first of all, how do I do this? So let me write down solution. So what is the equilibrium point? Equilibrium points. To find out the equilibrium points, what do we do? You do dx1 over dt equals to 0, and then dx2 over dt equals to 0. What do you get? You get x1 plus 2x2 equals to 0. There you will get 3x1 plus 2x2 equals to 0, right? So what do you get if you solve this? See, since there is no separate constant term, there is no constant term, so the equilibrium point will be just 0, 0, right? Because this is like x1 and then x2, there is no constant term. I mean, you can solve it. How do I solve this? You can multiply, you can just subtract, right? So multiply the first equation by -1. What do you get? So you'll get negative x1 minus 2x2 equals to 0, right? You cancel that one. What you get is 2x1 equals to 0. So x1 equals to 0. If you set x1 equals to 0, you will get x2 equals to 0 as well. So what do you get? 0, 0 is the only equilibrium point, right? Only equilibrium point. Let's say equilibrium point. Okay. Now we want to test the stability of that equilibrium point. So for that, what we do to test the equilibrium point, to test the stability of the equilibrium point. So we will talk about different method later, but for now I want to draw the direction field and the phase plane. How do I do that? So let me write the given equation in the matrix form. We have dx over dt, right? Vector equals to ax, just ax, right? What is a? Where a is equals to, how do I write that? It is like 1, 2, and then 3, 2, right? That is a. That is the matrix A, because you can write that as dx1 over dt and the dx2 over dt in one matrix, and then write like this, right? Let me show you just quickly. So how do you write this equation? You would write this equation as like dx1 over dt and then dx2 over dt, right? You can write this, the left side matrix. On the right side, you can write 1, 2, and then 3, 2, and then write x1, x2. You can write this way, right? So that's what I'm writing, dx over dt. For the left side, I wrote just d vector x over dt equals to a is that matrix, and then x is that x1, x2. Okay, guys. Now, so what do I do is to draw the phase portrait, to draw the phase plane, or to draw the direction field. What I'm going to do is I will take various points in the I will take various point there, okay, various xy point, because this is like x1, this is like x2, and then I will pick various points and then draw the direction field. But how do I draw the direction field here? It's just very easy thing. What we do is let us take 1, 0 there, okay? Let us take x equals to vector x equals to 1, 0. So what happens there? If you get if you put vector x equals to 1, 0, I mean, you know what? This is one thing that you can write. This can be written as x vector x prime equals to ax. You can write that way because x prime is dx over dt, right? So it will be easier just to write that way. So what do you get? So if vector x equals to 1, 0, then what will be x prime? Vector x prime is equals to ax, right? That will be, what is a? A is 1, 2, 3, 2, right? You can write parenthesis or bracket, no matter, is not a problem, okay? So it will be 1 is 1 comma 0. So what do you get? 1 times 1 is 1, 2 times 0 is plus 0, right? And then 3 times 1 is 3 plus 0. What do you get? You get 1, 3, 1 comma 1, and then 3, not over, 1, 3. So how do I draw a directed line then? We were talking at 1 comma 0, This is 1 comma 0. So 1 comma 0 point, it is taking to 1 3. So where does it take? It takes 1 3. Okay, so what we do from here is, this is the beginning point, and then 1 is, x is 1, y is 3, 1 2 3. So somewhere this direction, right? 1 2 3 will be somewhere here. So you will draw a directed line to that, towards that point. You don't draw that long, we just draw each line of the same length, although that does not give you the exact magnitude there, but it gives you the direction, right? Similarly, if you take, let's say 2 0, if you take x equals to 2 0 2 0, then you will see x prime will be ax again, right? You will write 1 2 3 2, and then you do 2 0, right? What do you get? If you multiply, you will get 1 times 2 is 2 plus 2 times 0 is 0, and then 6 plus 0, that will give you 2 6. Okay, so at 2 0, this is the 2 0 point, right? Let me use different color there. So this is point 2 0. Okay, from 2 0 you will have to write a directed or pointed line towards 2 6. You should count from here, not from here, not from the origin. You should count from here, 1 2, and then 6 will be 1 2 3 4 5 6. So it is again going that direction. Okay, similarly, where would that go if you take, let's say 1 1? Let's say this is 1 1, right? So let's do vector x equals to 1 1. At point 1 1, you will draw a directed line. So x prime will be 1 2 3 2, right? And then 1 1. Okay, so what do you get there then? So 1 times 1 is 1, plus 2 times 1 is 2, and then 3 times 1 is 3, plus 2 times 1 is 2. So you'll get 3 5. So basically you get 3 5. So from 1 1 you will go 3 unit to the right, and then 5 unit up. So it will be like 1 2 3, and then 1 2 3 4 5. So it will go like this. You see that? Similarly, you draw, you fill all those. Okay, all those one by one. Now, which is very tedious to do. Okay, so it is very tedious to do, but there are software. That's a good thing. There are online, you can say apps, I would say, on the same app that I was using when there was only one single differential equation there. So I have an app there. This is the website. You can basically just save this website in your browser, okay, so that every time you need, you can just open it and then say, what I'm doing here is, there is no x1 x2 in this app. What you do is, instead of x1 I suppose x, instead of x2 I suppose y. Okay, so it is like x plus 2y, and then 3x plus 2y. That's what I did. And when I do that, variable is y versus x. See, this is like x, this is like y. Okay, now you can pick the limit for x and y. The minimum value of x, this negative 4 to 4, and maximum value of y and maximum value of y. Well, let's do 4 and 4 again for both of those. Okay, now this is what you get. Now let me clear that. Now let us look at this. So this is all the direction field. Now, how do I know the solution curve? For example, if your initial value here, if your initial value is, let us say the initial value is, let's say 2 comma 0, okay, then how would that look like? The solution curve will look like this. Okay, if your initial value is, let's say 0 comma 1, okay, then what would that solution look like? The solution will look like that. Okay, it sounds like if you draw many curves, look at this. If you draw the many curves, see, if you click anywhere there, it will show that will be the initial value, initial point. Okay, and then it will give you, the app will give you the basically the solution curves. Now all these lines, or wherever you start, they are going away from 0, right? They are going away from 0. Okay, let us see another example. Okay, so what we want to do here is find the equilibrium points of the system, this system. Okay, so this is non-homogeneous, right? Because you see that there is a separate constant term other than the terms having with x and y. Okay, and this is autonomous, right? Also draw the direction field and phase plane to see the behavior of solution near the equilibrium point. So we want to see if the solution is going towards the equilibrium point or the solution is going away from the equilibrium points. Okay. All right. So let us do that. So solution is to find out the equilibrium point. What should we do here is we need to do x prime equals to 0 and y prime equals to 0 and solve. Okay. So what do you get? Negative x plus y plus 1 equals to 0. The other one is x plus y minus 3 equals to 0, right? If you add them, what do you get? You get 2y and then minus 2 equals to 0, right? So you get y equals to 1. Now you plug in y equals to 1, what do you get? You get negative x plus 1 equals to 0. You see that? So you get negative x equals to negative 2. So x is equals to 2. Okay. So what is the equilibrium point? Equilibrium point or equilibrium solution, I would say, is 2, 1. Okay. Now we want to draw the direction field for this. I want to use the app that I showed you. What do I need to do is I need to enter the right side of this and right side of that one. Okay. Let me see how does it look like. So I enter the right side of the first equation is negative x plus y plus 1, and the right side of this equation is x plus y minus 3. Okay. Now if you enter that and then if you set the x max and x mean, y max and y mean, okay, so you can pick the equal number of the pointed arrow. Okay, there. So what do you think? So you get this direction field, right? Now you see that 2, 1 is the equilibrium point. Okay, 2, 1 is the equilibrium point because there is 2 and then 1 somewhere here, right? 2, 1 is the equilibrium point. Now what do you think? Look at this. Let us draw a different solution there. You see that? If you draw various solutions, you see that all these solutions either go, so all of these solutions are going away, right? You see that whatever solution you draw, they're going away from the point 2, 1. Okay, so that's what you will be writing. Okay, so you will write that the solution curves in the vicinity of the equilibrium point point 2, 1, they go away, or you can say tend away, right? Tending away from the point. Okay, from the point. Okay, so another thing that I wanted to mention is that equilibrium point is also called a critical point. Okay, so it's the same thing if you say equilibrium point or the critical point. All right.